Alright, so really quick video here today on how to make an orthogonal unit cell. I'm only making this video because it's really not that hard of a procedure to go through if you're doing one cell. It's not that difficult to figure out by hand, but it is not fun, definitely not fun, one, and if you're doing it for a bunch of structures, you want a good way to do it. So the only things that you'll need for this are going to be ASE and ABTEM, so conda install C conda forge ASE, and then same thing for ABTEM. ASE is the atomic simulation environment, ABTEM is a TEM package, and it has one particular function that is useful for what we're doing. I don't use it for anything else. Okay, so I have a script that shows you this, and just to give you an idea, so obviously, if you're here, I'm not going to explain like what orthogonalizing a cell is, because if you click down in the video, obviously that's your goal. You understand what that is. But it is important to understand that this is going to work differently for different systems, right? So I've got two kind of representative systems for us. One that's going to work very well with this orthogonalization procedure, and one that's not going to work so well with an orthogonalization procedure. So basically, I'm just reading in, first off, the imports. This is the function from abtem.structures, import orthogonalized cell. From ASE.visualize, this is just for viewing purposes. ASE.build, that's just to give you this example silicon system. What you will probably want to import is ASE.io. Okay. Reason being, you presumably have your own structure, which you are trying to orthogonalize. So you just read it in like this. Name it something equals ASE.io.read, your structure's file name. Then what you do is you do orthogonal atoms. I'm just naming it orthogonal atoms, comma, strain. This will give you some information about how well the procedure worked for your system, equals orthogonalized cell. Pass in your atoms object, and you can leave this to true. So we're good there, right? And then I'm going to print out this information that tells us how well the procedure worked for our system. And what you would probably want to do is you would want to take your cell, or rather your new system, and write it to a file. So you just say, oopsies, hold on. It should be orthogonal atoms2.write. I would just name it whatever you had previously, underscore orthogonal. Okay, so let me run this now, and I will kind of show you what it's doing, and I'll show you also what to keep an eye out for. We're going to get a bunch of things popping up. You will only have this if you use those view statements. Okay. So we can see it took this silicon, which is not orthogonal, and it gives us an orthogonal one. We can see it took this GA203, which is not even close to orthogonal. It looks kind of very irregular. And it gave us something which is now orthogonal, right? So that's the goal. That is good. If you're using this purely for visualization purposes, if you want to just visualize an orthogonal cell for if you're trying to make a figure or something, then you don't care about this information, very honestly. You just get your new structure file, open it, whatever, make your figure, nice. If you care about, if you're doing this for the purposes of feeding into some atomistic simulation, then there are two things you want to keep an eye out for. So maybe you want to create an orthogonal cell so that you can interface it with a different orthogonal cell. It's kind of annoying and difficult to interface cells like this with each other. But say I wanted like a heterostructure where I have a layer of this followed by a layer of this. Then when I do that, I'm additionally going to have to strain one of the unit cells, presumably, right? Because they're not going to exactly line up in integer multiples. So, 3 cells of this is not going to equal 3 cells of this, for example. Meaning I'm probably going to have to strain one or both of the materials in order to get that to fit. And that's a problem, potentially, if it's a large amount of strain. Now, what this procedure does is it also applies strain, right? So for the silicon example, this is the strain. These are the diagonals of the strain tensor. There was no strain. There was no zoom, and there was no shear, right? Because obviously this is a pretty standard cell for silicon, right? So it's going to find that, and it's going to give you that, and there's no distortion of the structure. In the case of this very abnormal cell, though, there is, in fact, strain, right? There's strain up to 6%, a small fraction of a percent, and then, a huge strain here, followed by zoom and followed by shear again. This is what you would want to keep in mind, okay, because if we look at, for example, let's look at the bond length between this, 2.351, and it's 2.351, right, because we didn't strain the cell. There's no distortion, really, to the system itself upon orthogonalization. But here, let's try and kind of see, I believe, like this right here would be kind of like this right here. So, yeah, probably this is the right thing. I mean, if this is not exactly the correct bond angle we're looking at, then whatever, it's not really the point of the video. The point here is basically that if I look at the distance between these two atoms, 2046, whereas here it is 1894, 2044, right? So these things will change, and you need to make sure that they're not changing so much that your system is going to be physically problematic, especially if you are then going to be applying more strain to make a heterostructure type of system. So these numbers here will give you an idea of if that's a problem. Always inspect your own structure to make sure also, but that's really the entire point of the video. Again, it's very quick. I will close this and reopen the Python file for you here in case you want to copy paste this sort of stuff. Again, you would just read in your atom structure, orthogonalize it, and then write that orthogonal cell out, and then do whatever it is you need to do. So, yeah, I hope that this is helpful for someone. I know that it's kind of an annoying procedure, again, to go through by hand for a bunch of structures, so I'm sure that if you find this video, this will be useful to you. So thank you for watching, and have a good one.